Now we get to the grand finale of our lecture here, which is determining the field due to a disk of charge. Now, this is required by the AP objectives for AP Physics C. You got to be able to know how to do this. It says specifically you'll be able to do this problem. So we got to be able to do it, even though some of the results we'll be able to find much easier in later chapters. But let's do it this way anyway so we can appreciate how easy it is deriving it either with electric potential or with Gauss's law for when we're really close to this disk. But what I'm going to do here is I'm going to use this result that we got from the ring, and here's our disk. Again, it's got radius r right there. There's the radius r, big R of the disk. I'm going to use our result by just adding up the fields due to a bunch of rings. This ring right here is one example, and all the rings from r equals 0 all the way out, all infinite number of rings from 0, radius of 0 all the way up to big R. I want to add up all infinity of the fields due to each of these infinite number of rings. So notice that no longer does our ring have charge Q like it did up here. Each one has got charge dq because each of these rings is going to be infinitesimally thin. How thin? Well, dr is the width of each ring. There's got to be an infinite number of them, so they have to be infinitely small. So I'm just going to rewrite this. What I mean by this is I want to integrate all these over the entire disk. How am I going to get these rings over the entire disk? I'm going to change the radii of the rings. So the radii of each individual ring, r will range from 0 all the way up to big R. I'm going to add up all infinity of these rings. So I'm just going to take this relationship and rewrite it here. It'll be K. Instead of Q, each one only has an infinitesimal charge, dq. And X is going to be the same thing. And this is over, instead of x squared plus a squared, it'll be x squared plus, well, here's our ring of R. Whoops. So what is this length right there? Well, that's square root of x squared plus little r squared. So I got to put that right here. X squared plus r squared to the 3/2. And now the next step is I got to figure out how to express dq in terms of x or r. Okay. So, well, it looks like I'm going to have to integrate with respect to r, so I got to get a way of expressing this dq. How much charge is on this thing? This thing right there. Got to express that in terms of r, and I will also have to use the surface charge density sigma. So notice that in this situation, the dq is going to be sigma, the surface charge density, the number of coulombs per square meter, times what? The area of this infinitesimal ring. I got to find the area of that infinitesimal ring, which I'm going to call dA. It's an infinitesimal ring. Well, what is that dA? You might be tempted to say, oh, it's pi r squared outer minus pi r squared inner. But this only has one radius. This has infinitesimal. It's infinitesimally thin, so we can't do that. Here's how we actually figure out what the area of this ring is. All we got to do is stretch it out. So if you stretch it out like this, just cut it right there, okay, for example, and I'm going to stretch it out like this. What is the length this way? This is, well, let's do the easy part first. This is from there to there is height dr. But what is the length? Well, it's all the way around once. This will be 2 pi r this way, from there to there. The dA is going to be equal to this area right there, which is 2 pi r dr. We have to use this trick because it is an infinitesimal width. We don't have two different radii. Both those radii are the same. The inner radii and the outer radii are the same. So this is the only way we can figure out the area of that. So now I can express dq is equal to sigma times 2 pi r dr. Now what we're going to do is we're going to now plug this in so that we get the, we're going to integrate again from, so e at p will equal integral from r equals 0 to r equals big R. K, for dq, I'm going to put in sigma times 2 pi r dr. That's my dq. The x is still going to be in there. And this is all over x squared plus r squared, all to the 3/2. Now this may look like a really difficult integration, but they've chosen it because it does come out okay simplification wise. Let's go ahead and take out everything that's a constant. So that'll give us k times sigma times 2 from the 2 pi times x. And that's the only constants I can bring out. Let me see, I got rid of that one, I got rid of that one, got rid of 2 pi, got rid of x, and then times the integral from r equals 0 to r equals r of, all that's left is x, r rather, r dr over x squared plus r squared, all to the 3/2. So that's like x squared r squared to the negative 3/2. And when we integrate that, so I'll rewrite it so we can see this a little bit better. E at p equals 2k sigma pi x times the integral from r equals 0 to r equals r of r times x squared plus r squared to the negative 3/2 dr. Well, when you have an integral like this, you've got a nested function here, so we may need a correction factor. In fact, we do. So let's just, for example, if we just try, so I'm just going to try to see if, well, what happens if we have, if we think the integral is x squared plus r squared to the, we're going to add 1, so that'll be to the negative 1/2. Does that work? And this is how I'm going to find the correction factor. You may have another method of doing it. But if we took the derivative of that, so d dr of that would be equal to negative 1/2. Whoops, it should be on the outside. My bad. It should be negative 1/2 times x squared plus r squared to the negative 3/2. But then I have to multiply it by the correction factor, which would be using the chain rule times 2r. Hey, so interesting. That gives us, that cancels right there. So I got, hey, it works out. In other words, my guess was correct. So all I've got to do is, that's just for the integral, so I've got to rewrite this now as follows. So E at P is equal to 2k sigma pi x times, the integral will be x squared plus r squared to the negative 1/2. And I've got to deal with that negative sign somehow. So I'm going to make it a negative to begin with. And I'm going to evaluate that from r equals 0 to r equals r. So our final result here, we're getting really much closer, is this. We've got E is equal to 2k sigma pi x. Final will give us negative x squared plus big R squared to the negative 1/2. And then I subtract from that, when r is equal to 0, that'll just be minus x squared, or minus negative x squared to the negative 1/2 goes in here. This becomes a plus to the negative 1/2. So what does that give us here? That's x squared 2 raised to the negative 1/2. 2k sigma pi x times 1 over the square root of x squared, so that's 1 over x minus 1 over x squared plus r squared square root. So when I multiply this x through both sides, what I get is, and this is our final answer, E at P is equal to 2k sigma pi. When I multiply x, distribute x, I get 1, and then I get minus x over square root of x squared plus r squared. Not much simpler, but you'll see why I wanted to do this. So here's our final result. That is not that pretty, but that is correct, and here's why it's useful. As x approaches 0, look what happens to this. Well, if this is 0, then this thing on the bottom, this whole thing will be 0. We get E at P equals 2k sigma pi. This over here just kind of goes away because x is 0, and that's what we get. Notice how I can rewrite this. I'm going to rewrite this as follows. That's 2, k is 1 over 4 pi epsilon naught, sigma times pi, and pi cancels, and we end up 2 cancels 4, it's 2, so we get E as x approaches 0 is sigma over 2 epsilon naught. This is the field right next to a charged insulator. So that's assuming it's a uniform field, but when we get really close to this thing, it's like just like we're on the surface of the Earth. It looks like it's infinite in both directions. This works. So in other words, we have just verified this field, which we're going to find out when you're very, very close to the disk. The field is sigma over 2 pi epsilon naught. We're going to verify that next chapter for the C kids with Gauss's law. All right, that is almost everything that we've covered. So this is we're getting into the big time here. Be patient with yourself, have a lot of compassion, and enjoy all these challenging problems. And I will see you next time.